Chapter 6, Lesson 5 of Advanced Algebra, we're going to look at some more theorems about polynomial equations. And we do want to talk about one thing that we will be doing once we talk about these theorems. We talked about in the last lesson where we can use the rational zeros theorems to determine the list of possible rational zeros. And then we can use the remainder theorem to determine which ones out of that list are actually rational zeros. And I mentioned a number of times that while we were using the remainder theorem to determine which of those zeros were rational, that we were not determining all of the zeros, that there were possible other zeros that we weren't determining. And what we want to do in this lesson is talk about those other types of zeros, and then we'll wrap it up by showing how we can then, once we've applied the rational zeros theorem and the remainder theorem, how we can then move forward and finish off by finding all of the zeros that any polynomial has. So we'll first talk about the irrational and imaginary root theorems and how that helps us. And then in the next video, we'll put all of that together. We'll use the rational zeros theorem, the remainder theorem, and these two other theorems to help us determine all of the zeros of a polynomial equation. So let's talk about the irrational root theorem first. And an irrational number, you remember, is simply a number that isn't a perfect square root. In other words, the square root of 3 is an irrational number. Square root of 7, square root of 11, square root of 5. All of those are irrational numbers because they're not perfect squares, and so they come out to be an irrational number, which is a number that goes whose decimal doesn't repeat and doesn't terminate. Now, one thing you need to understand, that irrational numbers are also on the x-axis. And remember that x-axis represents all of the real numbers, and real numbers include both the rational numbers, which we talked about that theorem and how we figure out those, but that x-axis also includes the irrational numbers, all of these square root numbers. And so while the rational numbers are places where the graph will cross or touch the x-axis, irrational numbers are also a place where the function graph will cross or touch the x-axis. All right. So let's take a look at this theorem and what it tells us. It says if we have a and b as rational numbers, meaning a and b are not imaginary, and the square root of b is an irrational number, then if a plus the square root of b is a root, then its conjugate is also a root. And you remember we talked about conjugates when we talked about imaginary numbers, that we change the sign of that imaginary part. Well, with imaginary numbers, or excuse me, irrational numbers, we change the sign of that irrational part. Meaning, if I know that 1 plus the square root of 3 is a 0, or a root of a function, then 1 minus the square root of 3 must also be a root of the function. These conjugates, they always come in pairs when we're talking about roots. So any square root, if it's a 0, its conjugate must also be a 0. So 4 plus 3 square root of 7, if that is a root of a function, then 4 minus 3 square root of 7 is also a function. So these irrational roots will always come in pairs when we're talking about equations, polynomial equations with rational coefficients, okay? So that's the irrational root theorem. So the types of problems that you'll run into, or what we'll ask you to do, is we'll give you something like, let's say if the square root of 11 is a root and 2 minus the square root of 3 is a root, what other numbers must also be roots? And you would just give the conjugate. So if square root of 11 is a root, then negative square root of 11, its conjugate, is also a root. And if 2 minus the square root of 3 is a root, then 2 plus the square root of 3, its conjugate, is also a root. Okay? So that's all there is to that. So those are always going to come in pairs. Now, the imaginary root theorem is very much like it. In fact, it's almost identical. And it says that if these imaginary roots, they also come in pairs. Now remember, if we're talking about the x-axis and we're talking about rational numbers and real and irrational numbers being on that x-axis, you remember imaginary numbers are places where it's a root of the equation, but it's a place where the graph does not touch the x-axis. So if you have a graph of a polynomial equation and it never touches the x-axis, this equation does have roots, but those roots are going to be imaginary because this does not touch the x-axis, and only real numbers are on the x-axis, those irrationals and rationals. And the imaginary root theorem says that these also come in pairs. So if 4 plus I is a root of the function, then 4 minus I must also be a root of the function. So they come in pairs just like the other one. So these always come in pairs. All right, so if 3 minus I square root of 3 is a root, what else would be a root? 3 plus I square root of 3 would be a root because they always come in pairs and their conjugates are always roots. So these two theorems kind of tie together. When you're talking about irrational numbers, those will always come in conjugate pairs. And when you're talking about imaginary numbers, those will also come in conjugate pairs. All right? So that's all you'll need to know about these two theorems in this lesson, is being able to give the conjugate that those would also be roots. All right? So that'll wrap this video up. In the last video now, we'll put all of this together and look at how we can use the rational zeros theorem, the imaginary root theorem, the irrational root theorem, and use all of those together to find out all of the zeros of any polynomial function.